Alrighty. This lecture, we're going to discuss the next topic, um, which is kind of a shift away from how we solved problems in physics before, which is kinematics and Newton's laws and things like that, to kind of a new way of thinking about physics. And in fact, it follows Newton, of course, did physics, basically invented physics the way we know it today through the use of the laws of mechanics, Newton's laws, F equals ma, and kinematics. And he didn't know about the things we're about to start discussing, which is work and energy and things like this. This was invented after Isaac Newton. And so it really is kind of a shift in how to think about solving problems. And I believe I had mentioned it in a previous video how there tends to be like little groups of methods to solving physics problems. And we went through two. Kinematics is one method, Newton's laws is another method, and now we're about to get a third method, which is talking about energy. No specific method is best because it turns out not every physics problem can be solved by one of these methods. Certain problems are more easily solved by one method or another, but it's not like you could just say, okay, from now on, we're only ever going to use the energy method and solve everything in physics with that and don't worry about anything else. We can't do that. If we could, that's what we have already started doing, and we wouldn't have taught you everything else. So I mentioned all of this just so you get into the mindset of realizing that while the math is going to be the same and, you may or may not have to worry about components, the equations are going to be different, and it's kind of a different way of thinking about things. So the first topic is called work. And physicists have a very specific way of thinking about work that's not necessarily intuitive. For instance, in our everyday life, we say, okay, well, you pick up some weights, you go to the gym, you lift weights, you do so many repetitions, so many sets, whatever. Afterwards, you're sweaty, you're tired, your muscles are aching, and you can say you worked hard. You did a lot of work in building your muscles and in lifting the weights and such. But a physicist would say, no, actually, you did zero work whatsoever. And it all has to do with how work is defined in physics rather than how it's commonly used. So it's going to be something you have to get used to. First of all, I'll start with the equation for work, and that is W, work, is equal to force times distance. Very easy equation. Kind of like F equals ma, very small equation, easy to remember. But there's a lot in this equation that you maybe will not necessarily see right at the beginning. First of all, the unit for work is called a joule, capital J, joule. And a joule is defined as a Newton meter. And if you want to keep going with it, a Newton, if you remember, was kilograms meters per second squared, so a joule is a kilogram meter squared per second squared. So this set of units right here, physicists developed a shorthand, a little nickname for it, and they called it the joule, capital J. So that'll be the unit for work and in the future for energy. And another thing we need to keep track of is the fact that force is a vector, distance is a vector, and we're multiplying two vectors together. We have to be very careful about this. If you remember, when we first started talking about vectors, I said the rules of mathematics for vectors is different than what we're used to. We're used to scalars, numbers. We know how to add and subtract numbers, but when we try to add and subtract vectors, we couldn't do it the same way. we found that you can only add vectors together if they're in the same direction. And that was a big limiting problem for us. And in fact, it forced us to come up with the whole components, break a vector up into components, add the components together, and then combine everything together as a magnitude and a direction. That was a way of getting around the problem of adding vectors is not as easy as adding numbers. Well, it turns out multiplication is the same thing. The rules for multiplying vectors is not the same as multiplying numbers. It would be nice if it were the same, but it's not. So, of course, we know how to multiply a number. 3 times 5 is 15. And, of course, 5 times 3 is 15. That's commutative. Well, it's also, we know there's associative and distributive. There's a bunch of rules for the algebra of numbers, how to multiply numbers. Well, for vectors, it's kind of strange, but it turns out there's more than one way of multiplying vectors. Completely different ways. Not just like, well, you could do it this way, or there's a different set of steps to get the same thing. No, it's different versions of multiplying. And so I want to talk about that. First of all, if we have a vector, call the vector v, the first type of multiplication is just multiplying it by a number. Okay? So for instance, if you have the vector v, where v is 2 meters at an angle of 30 degrees, and you multiply this by 4, what it does is it multiplies the magnitude by 4. And so your vector gets longer, but it doesn't change the angle. You're basically lengthening or shortening the arrow, the vector. This is called scalar multiplication. You're taking a vector and you multiply it by a number or a scalar. It's one way of multiplying, but what you're doing is not multiplying two vectors together. You're taking one vector and you're multiplying it by a number. The next one is where you have, let's say, two vectors, A and B, and you want to multiply them together. Well, this way of doing it, we show the operation as a dot. And this is called the dot product. Also, some mathematicians will call it the inner product. So the dot product is a very special form of multiplication for vectors. And the way I want you to think about it is like this. Let's say we have two vectors. We have one vector, let's say this is A, and we have another vector B, like this. The dot product between these two vectors can be thought of like saying, take how much of B is in A's direction. So that's like saying vector B, what's the A's component? How much of B points in the same direction as A? So you take that amount and you multiply it by A. So instead of multiplying the actual length of B times the actual length of A, you're going to say, well, I only want to know how much of these two vectors point in the same direction. So I'm choosing A to be the direction. That's arbitrary. I could have chosen how much is in B's direction. But we pick one, so we say, okay, A will be the main direction. So how much of B is in A's direction? It's also like saying the parallel component of B that's in A's direction. So we would take that amount and multiply it by A. And we'll get some number. We could call it, I don't know, R, whatever. Now there's a way to do this, which I'll show you, but the main point I want you to truly understand is when you multiply A times B, it's the same as saying how much of A is perpendicular to B, or how much of B is not perpendicular, I'm sorry, parallel. How much of A is parallel to B, or how much of B is parallel to A. How much of these two vectors point in the same direction. It's all about same direction stuff. Now, one big rule that you learn in math when you talk about this form of multiplication is a very interesting thing, and that is you're taking a vector A and you're taking another vector B. You do this form of a multiplication, and the answer you get is not a vector. So this is a vector, this is a vector, and what you get is what's called a scalar, a number. So it's weird. It's like, okay, 20 meters per second in the x direction and 10 meters per second in 30 degrees north of east. I multiply them together, and I get, I don't know, 45 meters per second. It's just a number. There's no direction to it. You've lost the vector part, and all you have is a number at the end. Okay. Well, this is important because what it says is if work, sitting here, this is a dot product, because of course I've got the dot as the operation. That means when I calculate work, work is not a vector. It's always going to be a number. And the same you will see will hold true for energy. Energy will be a number, not a vector. So that's the dot product. And like I said, when we start doing examples, you'll see how to actually do it. It's very easy. So don't be concerned at this point. I'm just kind of going over. The last type is if you take vector A and you multiply it by vector B in what's called a cross product. So it's denoted by this X, cross product. And so it's kind of interesting when you're going through school, at least I remember in grade school, you learn multiplication, and the first way you learn multiplication looks like 3 times 5. And then, maybe the next school year or the year after, all of a sudden the teacher starts doing 3 times 5 with a little dot. And you're like, well, why aren't we using X anymore? Why dot? Well, it's neater, or whatever the reason. And then you learn 3 times 5, things like this. And they all mean multiplication. Well, that's true if we're talking about numbers. When we're talking about vectors, this symbol is different for the different types of multiplication. This is a dot product. You do a dot product a very specific way. The X is a cross product. You do a cross product a very specific way, and it's not the same as a dot product. So be very careful when you're doing work in kind of higher level math, higher level science. We can't use these symbols willy-nilly anymore because they actually mean very specific things. So the X means a cross product. And when we take the cross product, it's basically the opposite of the inner product, or the dot product. The dot product was all about how much of one thing is in the other guy's direction. So the two things, you want the components that are in the same direction. For the cross product, you want perpendicular stuff. You want one vector, how much of that vector is perpendicular to the other vector. And once you have that, that's what you multiply. And so when we talk about cross products, the most famous example in physics is torque. Torque is, most people understand it from either wrenches or screwdriver. You put a lot of torque, or cars, high engine, puts a lot of torque on the wheels, whatever. What it basically means is the force which is going to cause a rotation. And so if you think about, let's say, a bolt, and you have a little wrench, if you want to rotate this bolt using the wrench, how would you apply the force? Well, I dang sure wouldn't apply it downwards like this. That will make the bolt rotate. You're just pushing down. It doesn't do anything. But if I push this way, that causes the wrench to want to rotate this way, clockwise, and that will turn the bolt. And so when we say perpendicular, notice that there's some distance from the location of this bolt up to where the force will be pushed. That's called a distance r. And the actual force itself points in some other direction. That'll be the force F. And if the force and the distance are perpendicular to each other, you get a torque. Because it's only the force which is perpendicular to this distance which will give rise to the torque, a rotation. If I push a force in the same direction, parallel, I don't rotate anything. I just push. And of course, if I push with some angle, it will still cause a rotation, but notice it's only the amount of this force, if I break it up into components, which will be perpendicular, that counts. So that's how you want to think about cross products. The formula for torque is R cross F. The distance from the point of rotation to where the force will be applied. F is the force you're applying, and you're trying to multiply how much of those two vectors are perpendicular to each other. Okay. So for now, until it's necessary to understand how to actually physically do the multiplication, just understand dot product means parallel, how much of the two vectors point in the same direction. Cross products talk about perpendicular directions. All right, so we now know there's such a thing as different types of multiplication for vectors, so we have to be careful about how we do these things. But let's talk about work specifically. Again, the equation work is force times distance, where the times, the multiplication is called a dot product. What is an example of a nice little work problem? Well, let's take a nice flat horizontal table, and I place a block on a table whose mass, let's say, is 10 kilograms. I push on this block with a force of 100 newtons. Okay. What's going to happen? Well, we remember from Newton's laws, obviously, especially if there's no friction in this problem, if you apply a force to a mass, the mass will accelerate. So I know this block is going to move to the right. Well, I can ask the question. Let's say you're continuing to push and the block slides to the right while you're pushing a distance of 5 meters. The question is, how much work is done on the block as it slides 5 meters to the right? Okay. So this is a work style of problem. You're given an object, forces are applied to the object, it moves a certain distance. You want to know about the work done. Well, let's do the problem. Work is force times distance. Again, this is parallel stuff because it's a dot product, so look at the distance. What's the direction of the distance? The distance is 5 meters in the x direction. So, if I know that, then the only force I use is the amount of the force that's in the same direction. So that means I only want to know how much force is in the x direction. Obviously, if you remember, gravity is still here, but notice gravity is in the y direction. It's pointing downwards. I only care about how much force is in the x direction for this problem. So I say, well, my force is 100 newtons, and it's already in the x direction, so it's 100. How far did I go? 5 meters. So 500 joules of work is done. Really nice. Let's try another example. Again, nice horizontal table, block, 10 kilogram block. I apply a force of 100 newtons. And the block again slides to the right 5 meters. How much work is done here? Well, we go through the steps again. First of all, I know this is a work problem because it deals with forces and distances. So I say work is force times distance. But since it's a dot product, I'm talking about parallel force. How much of the force is parallel to the distance? The distance in this case, I'm moving in the positive x direction. So I want the component of the force, which is in the x direction. Well, notice this time my force is pointing in the y direction. And so I remember from vectors, if my vector is in the y direction, it's got no component in the x direction. It's 0. If it were at some angle, then I could do the sines and cosines and get my components. But here, since it's already in the y direction, well, there's no x component. So it's just 0. You do no work here. Well, that's interesting. It's kind of weird because no matter what, you are pushing with 100 newtons. You're applying a force, yet for this problem, you do work, and this problem, you do no work. And this is kind of the thing that's different about the physicist's definition versus the normal common parlance. It's not about how you feel. It's not about if you get tired. It's purely defined as if you do force, if you apply a force, and that force is in the same direction as the motion of the object, whether it's in, positive x or negative x, in the opposite direction even, then some work is being done. If the force that you're applying is not at all in the direction of motion, it's in the perpendicular direction, then you're doing no work. Even though you're pushing, that doesn't mean you're doing work. Now let's take that further. Let's do another example. This example is in 2 pieces. We have a block. I push with a force F1 of 100 newtons to the right, and that causes the block to travel to the right 5 meters. Then, once that's done, you then start pushing on the block the other way, giving it another force, F2, of 100 to the left, and that causes the block to travel back to the left a distance of 5 meters. The question here is, what's the total work done? Well, there's 2 ways we can think about this. The first way of thinking about it goes like this. When I do work is force times distance, this distance is really called displacement. It's a fancy physicist version of distance because it's the vector version. And what it really means is, what's the difference between where you started and where you ended? So, for the first case, I was at the starting location, I ended up 5 meters to the right. So the displacement, the distance, is 5 meters. For the second piece, same thing. I'm starting in some location, I end up 5 meters to the left. So what's my displacement there? That displacement will be -5, because it's 5 to the left from where I started. So the total displacement is the sum of those two displacements. I was here, I went 5 to the right, then I went 5 back to the left. So I 5 minus 5, or 5 plus negative 5, really. So the total displacement would be 0. So the distance, the displacement is 0. And then so it doesn't matter what the force is. Whatever the force is, I don't care. I'm multiplying by 0, I get 0. No work done. Another way of thinking about it, is this displacement thing, is to say, forget about the fact that this happens in two pieces. Let's look at the beginning and let's look at the end. At the beginning, I'm at this location with a force pushing on it of 100 to the right. How do I end up? Well, something happens and then something happens, whatever. I end up right back at the same location. So what's the difference between where I start and where I end? There's no difference. I started here, I ended here. I'm no different from where I started. So the distance, the displacement must be 0. So I do 0 work. Same basic concept. The first one talked about adding the different pieces of displacement together to get a total displacement. The second is just saying, don't worry about the pieces. Where did you start and where did you end? Both ways of thinking about it lead you to the same conclusion. No matter what you do, if you're applying forces, the object moves around and the object comes back to the same starting point, you've done no work whatsoever. And that's kind of like what I meant when I talked about the gym, lifting weights and stuff earlier. We would say we did a lot of work because we're tired afterwards. We actually lifted the weights. But a physicist would say, well, no, the weight started in the weight tray, the bar where all the weights are. You did stuff, but then they ended up right back where they started. It's as if you didn't even go, according to how things look, how things started and ended. So you, in fact, did no work. So you have to be careful when calculating work to understand things may look like work is being done, but mathematically, if you go through the math, you're actually doing no work, or you're doing less work than you thought you were. All right, so now, just to be clear about it, work is not being done, number one, if the object ends where it started. And number two, work is not being done if the force that's applied to the object is perpendicular to the distance. However, it's possible that you apply force not directly parallel, but at some angle, and still doing work. And that's the next example I want to show. And that's, the most interesting, obviously. Let's take the example of a block on a table again. Here's my table. And this time, I'm going to push with a force, F1, of 100 newtons at an angle of 30 degrees downwards like this. And let's say in doing that, the block slides to the right a distance of 5 meters. What is the work done? Well, we handle this just like we handle the other problems we've done. First question is we say, okay, well, what's the direction of motion? In which direction does this block slide? Well, obviously the block slides in the positive x direction. That means the force that I'm about to use in work equals force times distance better be an x directional component. So let's look at my force. Is the force in the x direction? No. Is it perpendicular? Is it in the y direction? No. So it's not 0. Because it's at an angle, I'm going to have to do my little component trick, which I've been having to do. So let's make a little triangle out of the force, just like we always do. Here's the x side, here's the y side. And so I would say our force has an x component and a y component. The x piece, the x side is the side adjacent to the angle. Adjacent means cosine, so it's 100 cosine 30. That force is pointing down and to the right. To the right means it's a positive force in the x direction, so it's positive, 86.6. The y component, may as well write that down too. The y side is opposite, so it's sine, 100 sine 30. F1 is pointing down and to the right. In the y direction, it's down, so he's negative. So we get negative 50. Okay. So all the forces in my problem, I've broken them up into x and y components. I can now solve my problem. I say how much of the force is parallel to the distance. That means for this problem, the distance is x directional, then I only want the x directional force. So I would take 86.6 times the distance of 5, get out my calculator, type it in, and I get 433 joules. So you can see, not a big deal. You can also see why, and I say this almost every lecture, why we spent so much time at the beginning of the semester concentrating on vectors, being able to do components, because here, again, components pop up. They pop up all the time. And if you can't do components, you're always going to be getting these problems wrong because you're using numbers that are inappropriate. But if you are used to components, then it's easy. Break everything up into components, and then just choose the components that are necessary for the problem. This problem, the x direction was the important one. Why? Because the direction of motion was in the x direction. Now, I want to do one more example, because one little aspect of it I haven't described is when is the work positive and when is it negative? Thankfully, that's kind of an easy question. If the force is in the same direction as the motion, it's positive. If the force is in the opposite direction, that is to say, let's say the block slides to the right. If the force is to the left, it's still x direction, but it's in the opposite direction, then it's a negative work. So let's see an example with this. Let's say we have the table. Here's our block. I apply a force of F1 is 100, and let's say F2 is 50 at an angle of 30 degrees downwards like this. And with these forces applied, the block slides to the right a distance of 5 meters. Find the total work done. Okay. So there's two ways of thinking about this problem, and they're equivalent, but I'll just tell you what the two ways are. First way is to say, if there are multiple forces in the problem, then you can find the work done by each force separately, and then to get the total work, you just add up all the single works together. So let's try it like that. What's the work done by the first force? Well, okay, what's the direction of motion? The block moves in the positive x direction. So x directional forces are what I care about. F1, is F1 an x directional force? It is, so we just stick it in. 100 times 5 gives us 500 joules. What about work F2, which is the work done by the second force. Again, the direction of motion is still the positive x-axis. However, now our force is not an x-directional force, it's at an angle. So I can only use the x component. Well, what's the x component? It's 50 times the cosine of 30. So that's the x component of my force. The distance is 5. And now we worry about positive or negative. In this case, the work done is negative. And it's not simply because F2 points to the left. Okay? The reason this is negative is because force 2 points to the left, but the direction of motion is to the right. They're opposite directions. So because they're opposite directions, I put a negative. This negative is not because F2 is to the left. For instance, if F2 is to the left and the block slides to the left, this would be positive. It's negative because they're in the opposite directions. For instance, let's say F2 were to the right, but the block slid to the left. Again, this would be negative. Even though F2 is to the right, because it's in the opposite direction to the motion, the work done is negative. Okay, so positive or negative is all about, are they both in the same direction or are they in opposite directions? Same direction, positive, opposite directions, negative. Anyway, I'd get out my calculator, I'd say 50 cosine 30 times 5, and I'd get negative 216.5. And then the total work done, of course, would be 500 minus 216.5. 500 minus 216.5, and I get 283.5 joules as the total work done. I add up each individual work one by one, and I get a total work. That's one way of thinking about it. The other way of thinking about it is to say, well, just put it all together at once. Work is force times distance, but we could think of the force as adding up all the forces together. So we could say, okay, all the forces that are in the x direction. Well, I've got 100 to the right, and I've got 50 to the left, but I only want the x component, so it's 50 cosine 30. And then those are all the x component forces together, and I multiply by the distance, which is 5. So when we do it this way, we get 100 minus 50 cosine 30 times 5, and I get 283.49 joules. Same thing. So whichever way you like doing it, either way is fine with me. You can either stick all the forces in at once and multiply by the distance, or calculate the work for each force individually and then add all those up together. But this shows you how to calculate work. When are the works negative? When are they positive? If you have multiple forces, how do you handle it? Well, you're just adding them all together. Now, of course, all the examples I've shown so far, everything's horizontal. But of course, you could have the same thing where you have a wall with a block and you push on the force. You push with a force and maybe the block slides up. Well, obviously, you're going to work it the same way. The only difference here is, for this problem, the direction of motion is a y direction. So here, you only care about y-directional forces. So just be careful about that, but, that's not a big deal. The main thing is calculating work talks about the force and the distance parallel to each other, in the same direction. So that's all I have for work. The next lecture, of course, I'm going to have example problems, but the next topic will be energy conservation, and that builds off of the work. Okay. So, as always, practice the problems that will be posted on Canvas. Keep up to date, and until next time.